没有的啦。
啊？杠错了。
啊？
杠117。
怎么没抓下来啊？他们是听解的。
听解。
知道呀。我才5
才接什么？哎，我有可能。It's okay. We don't
right.
I just wanted to. Yeah. Sure.
你可以知道那个地址啊，你可以知道那个地址，你要知道那个地址。
这个我好像我去看一下。你那个是内部广告之前那个吗？
他的 discussion strategy。
我先上去。
It's not
not actually in the root of it, but it's in the simple DB folder. So you would have to CD into the branch plus the root. So that's fine. Okay.
We suggest you to put it just directly on the root.
Oh, so you want it directly on the root?
Yeah.
Okay. Okay. You can make that change.
All right, folks, let's get started. So, first thing first, you all know project 1 is due today. The lab 1 assignment is due today at 5 p.m. So in order for you to, some of you asked us this question, how do I know you have received our submission? You don't, as a matter of fact, you don't need to submit anything, you just need to commit. Right? It's a private repository that you and your teammate have access to, and just remember to add TA's Bitbucket account to it. And we wrote a little, Zhou Yue, one of our TAs, wrote a little script to automatically check the status of your commit activity on your repository. And we have this page. You can check back in yourself as well, if you remember this URL. And it shows basically the commit hashtag at the latest time of your commit. Okay, so you can just use this to check, sure that you have something successfully committed. Okay, and the timestamp. At the end of the day, we will be using this particular timestamp to check whether you have made a submission of, in other words, a successful commit to your private repository by the deadline at 5 p.m. today. Does that make sense? Okay. Now, clarification on the submission. Some of you read this question on Canvas. We specifically reply. I have asked Julia to send a broader announcement as well in case you haven't been keeping track of what happened on the discussion thread. So the way you do the submission is you make sure your source code is in the root directory of your repository. Okay, and make sure you commit to a branch called project1, PROJ1. Okay, making a branch called PROJ1, and make sure the source code is in the root directory of your repository. Okay, any question regarding this? As always, if you are not sure whether you're doing things, according to what we asked you to do, then just read the question on the discussion thread or send us an email. Okay? Any question on the submission of your project 1? So let me do a show of hand. How many of you are still working on your implementation? Okay? Do you think you have finished by the deadline time? Hopefully. Okay. So the others assume you have finished your implementation of project 1 already. Okay? Alright. Now let's resume with our lecture discussion. So a quick recap of what we said last time. So we were talking about external memory model, meaning that you have to data transfer between memory and disk. And for the moment, we are ignoring the data transfer between memory and CPU, meaning memory and data cache. And in that case, a quick recap of this little example we used. This is a queue. In main memory, in internal memory, a push and pop operation take order 1 cost. But in external memory, if you were to use the same algorithm, you end up paying 1 I/O per item, which is fairly expensive. So what you should be doing is this buffering strategy, where you pop, you cache that page of data you're trying to popping data from, and you click on the page until every data item on that page has been popped. So, and similarly, you do the same thing for the push operation. If you do this, you can easily show that you got an order 1 over B, where B is the page size, B is number of data items fit into a given page. Then you got an order 1 over B cost, amortized cost instead of order one cost. Okay, that's what we said. Then we generalized this discussion to heap file and sorted file. We were halfway of filling up this table. Okay, so we're gonna continue the discussion from there. Okay, so now let's focus on range search. Suppose we have a heap file and suppose we have a sorted file. You call that n is the number of total number of records you have. So n over b tells you the number of data pages you have in your heap file or sorted file. In terms of the size capacity, the two are identical. It's just that on a sorted file, they are sorted out. For example, I'm trying to find student with student ID between 100 and 200. So that's a range search. I'm trying to find all such students with student ID between 100 and 200. If you were to do this on a heap file, what's the cost? Can someone make a guess? What you have to do? Matthew, can you do that? Do the range search on a heap file that the query I just posed, finding all students with student ID between 100 and 200. What would you do?
Sorry, give me a second. So range search to find all of the students with an ID within
100 and 200, yes, that's right.
Wouldn't it be similar to the equality search, right? Because you have to select all of them?
Yes, it's almost the same process as the equality search because they're not sorted in any way. So in order to find this matching record, you really have to go through everything. You have to go through the entire file to be sure you have examined every possible record to find a potential match. Does that make sense? So you have to scan the entire file to because if you don't scan the entire file, even if there's just one page of data you haven't looked at yet, that one page of data may contain a record or more records that satisfy your query condition. So you really do have to go all the way to the end for the heap file case. Now, with that being said, can someone tell me how do you do the same search but not using a sorted file? What's different here?
I would just find one
Okay.
record and then dance from there to the right or to the left.
Yes, that's excellent. To the right or to the left, depending on whether you're sorted in descending or ascending order. Okay. So let me repeat what she said. You do an equality search of the smallest value of your range search. In our example, it was a student with student ID equal to 100. Once you're there, the point is, if these are your pages, suppose they are linked lists together. We use a double linked list to link them together. And you are finding student ID. You're trying to find all such records, right? You're doing this, right? What you will be doing is you try to find a record with ID equals 100, and you find student ID. So within each page is record after record after record, which essentially is what you have implemented in your lab 1. So each of this is just a record. And the cool thing about the sorted file organization is they are sorted by student ID values. Let's say we're in this particular case we sort them by ascending orders, meaning a record with larger student ID value is to be placed towards the right side of your file. Okay? So what you do is you try to find this record, suppose it's here. So what can you do? What can you say about the following subsequent records? Well, they must have student ID strictly greater than or equal to this record. And all records to the left of this, on this page and on all of the preceding pages, their student ID values must be smaller than 100. you're sorted by student ID. With that being said, once you find this record, you can do a linear scan until you reach a page where this is the last record with student ID, or the first record whose student ID value is greater than 200. Let's say 201. At this point, you have stepped outside this range already. There could be absolutely no more records with value with SID value being in the range of 100 and 200 because they're sorted again. So what's the cost of this? What's the cost of this? Well, obviously you have to pay that equality search cost. In the best case, it's 1, as we analyzed last time. You're lucky the first page you're looking at contains that record. In the worst case, it's log 2 of number of pages. You're doing essentially a value search over the number of pages you have. That's the worst case. Best case is 1, worst case is log 2 of N over B. And then you just do linear scan. The question is how many pages you have to do linear scan for. How many pages you have to do linear scan for? Well, this depends on the size of your output and your page size. Suppose I tell you there are going to be T records using our notation. There are T records in the output. How many pages you have to scan for? Someone tell me now. Can you tell me now? Let me repeat my question, right? If I tell you we have T records in the output, how many pages I have to scan for? T over
number of records,
which is B. T over number of records on each page, which is B. So the total cost is just that. Number of matching pages, which is T over B. And this is simply N over B. Is that clear? Now the insertion and deletion for heap file, the operation that follows, you are trying to insert a single record into a heap file. What will be the cost? Guess? This is fairly straightforward, right? If you think about it. If I try to insert a record with some potential, some whatever values into a heap file, what's the cost? It's constant. Yeah, what is that constant? Let me be a little bit picky. It is constant. What is that constant? Well, just look at your implementation in lab 1. Remember, we are working in this model. We are working in this model. So, which means in order to write a particular record to a disk page, what's the first thing you have to do? You have to bring that page to memory, cache in the buffer, update that page, mark that page to be dirty, and eventually write it back. So that involves 2 I/O. So that constant is 2. Okay? For heap file, the insertion is just 2. What about for sorted files? Is it still 2? You said no. Can you tell me why?
You got to put it in the right place.
You have to put in the right place.
Find
Which
the
is?
right places.
Find the right place, which is the binary search, which is just like equality search. In the worst case, it's log 2 of number of pages, but you're not done yet. By the time you finish doing that binary search, what you have is that page, which is, in your word, the right place to insert record for is cached in the buffer already. You update the page, and you have to write it back. So there's +1 cost to it. So the total cost is simply 2 and log 2 N over B plus 1 respectively for heap file and sorted file. Excellent. Any questions regarding this? No? Okay. For deletion. Oh, let me explain this part. No, suppose that was the insertion cost. If you think about it, you can do this if you're lucky and in the sense that there is enough space left on this page, in his word, the right place. The page for the right place has at least one more slot left to insert your record for. Does that make sense? What if, in the worst case, There are no space left on that page, not only on that page, on all subsequent pages. That's really the worst case. But I'm trying to place a new record here. This is the right place. But there's no space, not only on this page, but on subsequent pages. Except maybe the last page. Last page I have some space left. What do I have to do? Well, in order to maintain the sorted order, you have to move all of the records from all of these pages forward by a set of a slot. Does that make sense? And what's the cost of that? Well, you need to read and write each page once. On average, you're touching about half the number of pages. But read and write times 2 of that essentially leads to this analysis. This is for equality search to find the right place. This is to cater for the worst case, and on average, in that worst case, you need to read and write about half number of pages. So 2 times half of an over D. That's how we come to this value here. Any question on this? Compact for sorted file means that there's no space left. That's what I mean by compact for sorted file. Okay, if you understand the discussion for insertion, it should be fairly easy for you to understand the discussion for deletion. To delete a record from key file, what would you have to do? Well, you need to first find the record to be deleted, which is essentially the searching cost, which is, on average is half of N over B, as we analyzed from last lecture. It's only find the page containing the record you're trying to delete for. By the end of it, that page is already cached in the buffer, but you do need to delete that record from the page, mark the page to be dirty, and finally write it back. So there is a +1 cost at the end of it. What's on this? Now, if you understand this, and you understand the discussion for insertion, for sorted file, similarly, that's the cost for deletion from a sorted file. You do a search, at the end of the day, you delete that from the buffer, mark the page dirty, that applies to indicate, to count. Of course, this is assuming you don't do compact operation for a sorted file, meaning that you are okay of leaving some space on this page. Suppose that's not okay to you. You want to 100% utilize the space you have, meaning that you want to make sure there's no empty slots in any given page. Then it becomes the searching cost plus moving all the records coming after the record being deleted forward, which you're reading and writing about half of the pages. Reading and writing times 2 of that gives you this cost, N over B. Right? So imagine you delete this, but you want to make sure there's no space left behind, not utilized. So what you do is you move everything forward from this page and all the subsequent pages. On average, you touch about half number of pages, read and write. You get that cost. Okay, so that's how we fill out this table. Any questions so far? Fantastic. Now we're gonna come back a little bit and look at this bigger picture here. So the objective, remember, for this course is for you to implement a database kernel. Okay, we just get started on that journey on lab 1. So in lab 1, you essentially have implemented part of your disk space management, part of the buffer manager, right? Part of it. Now, you haven't done any buffer replacement policy and all that. There will be a lab 2 coming up on that. And file and access method, you touch a little bit of this as well. You implemented keep file and keep file page optimizations per our discussion following what we said in the lecture. But really, these modules at the bottom of this stack is really to support the higher level modules, which is to support ultimately the relational operators in a database engine, and also to support the higher layer to do query optimization and execution. So I want to give you a little bit of an idea. Now, knowing how keep file and sorted file are organized in a database kernel, I want to give you a quick preview of how relational operators are to be implemented utilizing the underlying heap file and sorted file structures. Okay, later on, we'll have more in-depth, detailed discussion on that, but I want to give you a quick overview of that. So the query processing overview in a database engine is as follows. Pretty much, it's very similar, if you think about it, like how compiler works. Right? You guys probably have taken a compiler class before. So you write a program in C++, in Java, in any higher level language of your choice, and then that code you have developed will be pushed to a compiler to compile into code that the underlying machine architecture can understand. That's in a really high level point of view what happened in a compiler case. In database system setting, it's somewhat similar, surprisingly similar to that process. You write your program. We all know by now you should write your program in what we call SQL, structured query language. And then that program you have written will be pushed to a compiler-like procedure to compile into a representation that the underlying database kernel can understand and execute. So that's essentially what happened in the database part. And similarly to a compiler, you all know in compiler you do, at the compilation time, you do optimizations. Right? You do optimization. For example, you are in a loop, if you find some environment in a loop, evaluation, some statement to a constant, no matter which iteration of your loop you are at, most compiler will take that to evaluate outside the loop. So that you don't evaluate all the time. You evaluate once for all the iterations of your loop, right? Simple optimization like such. Similarly, in a database context, we want to do optimization as well. Meaning, given an SQL query, there are tons of different ways of executing that. Remember the earlier thing I said, database allow you to specify only what you want, but not how to do it. There are millions of different ways of executing the same query, and the efficiency of them will be all different. So the objective of the query optimizer, pretty much like a compiler, is to find out which is the most efficient way to execute a given query. Unfortunately, later on we will have a more in-depth discussion on that. This turned out to be a really hard problem. People actually show that if you are in the context of SQL, to find the optimal plan for a given SQL query is NP hard. So unless P equal to NP, we are hopeless in terms of finding an efficient polynomial time algorithm to always find the most efficient query plan for a given SQL query. So in practice, what really happens is the query optimizer will try to get rid of those really inefficient plans and find a good enough plan instead of always searching for the optimal plan. Because that may take very long time to do, which in itself becomes so expensive, which defeats the purpose. If you think about it, if the optimization process becomes so expensive, it defeats the entire purpose of doing optimization in the first place. You're better off just go with the regular plan and execute according to that, right? So that's the query optimizer on an input query and try to twist this input query to different query plans and find a good one for you. And once a query plan is fixed by the query optimizer, it will be pushed down to something called query executor, which take a query plan as input and execute the query accordingly. Let's look at a simple example. Let's say I'm doing this very simple query. Right? This is what we call a unary operator. If you think about this query, inside the kernel, the language the kernel understands is relational algebra operators. So the first thing is I'm going to translate this into relational algebra representations, which is projection of right? That's what I'm doing here. And note that in this translation, I don't have to worry about that keyword distinct because in relational algebra by default projection, which is pi, remove duplicates from the output. Okay. So what really happens, but if you think about it, even in this representation, I never really tell you how I am supposed to do the projection. There are millions of different ways of doing this, right? But which specific way I'm doing this? For example, you can remove duplicates by sorting. You can also remove duplicates by hashing. Which specific you're going to take? Well, it's not specified from this representation. So this is not a query plan yet. But this one I'm showing on this particular slide, that's a query plan. That's a specific query plan. What you do is you start with what we call a heap scan, which means you're doing a scan over a heap file. Suppose the student's table is represented by a heap file. Then you extract these two attributes, these two fields, out of each record while you are doing the scanning operation. And then they are fitted to the next operator, which is the sorting operator. You sort based on name and GPA. And then you apply the distinct keyword over it, which is to remove duplicates. In other words, for example, imagine if I have a, so to kind of give you an example of this, imagine I have the following records. What, GPA? So I'm gonna be nice to myself. Here. Okay. Alright. And so I don't want to be not nice to any of you, so I'm not going to use uname. So let's say somebody ABC 3.0 and DEF 3.5. Suppose this is like that, and suppose there's another DEF 3.5. Suppose that's the data I have. Okay? So what I will do is, well, of course, in addition to this, imagine each student record may have some additional record, like age value. Right? So suppose I'm 38, 17, and 18. These are age values. Suppose that's what happens. So if you look at that particular query plan, what happened is I'm going to do a heap file scan over this. And now suppose this is a page. So every page holds 2 records. So I have 2 records per page, and they're linked these together. So what this is doing is I pin this page to the buffer, and then do the projection. So after this, what you got is right, that's what you get. After that, extracting this record. Then you do a sorting of this. When you sort by name and GPA, what happens is you sort them by name first, and you break the tie using the GPA field. So this, let me change this to maybe 3.4 to make this case a little bit more interesting. So what happens now is if you sort them, you got ABC first, DEF 3.4, then DEF 3.5, and Feifei 4.0. Right? Note that the order of the two actually fits because I break the tie using GPA field. Then I remove duplicates by doing a linear scan of this. In this case, after they're sorted, I notice that there's no duplicate. The way I do that, I maintain a running counter to keep track of the current record value and just iterate through all the records. If the next one is the same as the one I remember in my counter, I cross over that. Otherwise, I just keep going. So imagine if I do change this back to 3.5, then I keep this. This is my counter value. The next one is identical to my counter value, so I skip that. I'll cross off that. Then I skip it. I go to the next one, so my final output will be that. So if you think about it, this is how database go from what you want, without specifying how to do it, to all the way how to do this. Of course, you may argue there are different ways of doing this, right? Instead of using sorting, maybe I can do a hash operation here to remove duplicates. Yet another approach is actually to flip the order of the two. instead of doing a heap scan and extract out those two fields, what I can do is I can sort everything together based on these two fields. Only afterwards I do the extraction and duplicate elimination. Right? Even in a simple case like this, there are so many different ways of doing it. The question is which is more efficient. And that's a unary operator. In the binary operator case, which is a join, right? So I'm joining two departments. It's even more complicated. Instead of it becomes a tree-like structure, as you can imagine. How do you optimize over this space? That's even more challenging. So for this purpose, database system introduced this interface called iterators, of the famous the volcano model. The idea is I'm going to represent a query plan using a set of operators, 1, 2, 3 in this case. And to implement each operator, I'm going to use a common interface. This interface is something like this. It has an initialization method. It has next method which returns a tuple when you call this method. And it has a close operator. And then it has an input array. When I write like this, this is C++ or C style coding, right? This ampersand means a reference. You can think about this as somewhat similar to just like a pointer. So what this does is an array of iterator references, or it has one or more pointers or referencing an address to other iterator class objects. That's what this does. That make sense? You may wonder why I need this. Well, if you go back one slide, think about how would you implement the sort operator. What would you do is you need a data source, which is that input array stands for. The input array basically captures all your data source. In most cases, it's just a size 1 array, because you just need one more iterator, another iterator to be the input data source for you. But in a case of join, to implement this operator, you need two iterator interfaces to two different iterator objects. Does that make sense? So the input array for the join operator will be reference to this and reference to this. Now, why you need a next method? Well, the point of next method is to keep feeding the next tuple to the next iterator in this pipeline. If you can think of this as the pipeline evaluation. So you keep grabbing, for iterator coming later in the pipeline, you keep grabbing a tuple at a time, or a record at a time, from the preceding iterator in the pipeline. And that's the reason why people call this volcano model. If you think about how volcano erupts, it's one after another. Right? The lavas flow out of it is one after another. They go in order. They don't go in random order. After they have erupted, yes, of course, they can flow in all random directions. But before that, they all go through this cone shape and form this particular pipeline, and they kind of go one after another. That's why people call this the volcano model of evaluations, and that's why you have that next operator. And this is a fairly generic interface where you're gonna instantiate this to the implementation of different operators. Okay? Let me give you, I don't have a. So that's essentially what I'm talking about. Summarize my discussion on this particular slide. There's an example of this, of hash join. So you have two sequence scan, and this feeds tuple into the join operator. Then you have a group by hashing operator on top. And we'll be talking about the detail of this later on. But for now, you can just kind of imagine the query plan is represented by a tree-like structure, and every operator, every node in the tree is an operator implemented by that iterator interface, and that's essentially what you need to know. Here is a concrete instantiation of that discussion, right? So if you want to implement a heap scan operator, now you want to do the scan operator, what would you do? Well, in the initialization method, you set up some internal state, some internal state number of variables, and you open the file. That's pretty much what you do in the initialization part of it. And next method will basically go through every page in new file and keep popping record one at a time. That's essentially what the next operator would, next method will do. And when you call the close method, it will close the file and maybe clean the buffer as well, unpin the pages essentially. Does that make sense? And you may also, what do I mean by internal state? Well, depending on the particular operator, you may have different number of variables. For example, for a scan operator, you probably want to have a Boolean expression, such as student ID greater than 100, less than 200. That's a operation-specific state you want to keep track of. Okay, so that's what we mean by quote-unquote internal state. So, and also maybe projection list, right, which change from one particular operation to another operation. You need to keep track of that using a member variable of this operator class. Okay, any question on the volcano model before I proceed? Okay, fantastic. So one note I want to mention, which I'm not going to go into detail right now, but maybe toward the latter half of this course I will be discussing about that, which is the picture quickly is changing quickly, given the landscape of architecture and compiler and PL has changed dramatically in the last decade also, right? Why I'm saying that? If you think about the volcano model, it actually makes sense in the I/O model, in the external memory model, when the bottleneck is really the I/O of pages to the buffer and pinning the page and doing replacement. But assuming, given what we said last lecture or 2 lectures back, we said NVM, non-volatile memory, and all that stuff, right? The changing the memory technology and how that may affect the design of database. This is one place those architecture change and compiler change may impact the design of our database systems. Suppose you are using NVM, non-volatile memory. So you no longer need to worry about durability and all that stuff, right? You're never gonna lose your data because you have NVM. And at the same time, you enjoy really fast access speed, like you have in the RAM model, random access model. So the bottleneck is no longer the I/O between disk and memory, per se. In that case, obviously, what will be the bottleneck? If you allow me to rewind a little bit. And then if we get rid of that top, get rid of this player altogether, the bottleneck will be the data transfer between memory and your CPU cache, your data cache. Right? So in that case, your bottleneck become the number of CPU instructions you have to do, as well as your cache coherence. How many times you have to bring a cache level data from memory to your CPU cache, and also the number of CPU instructions you have to do. In light of that, in that particular setup, the volcano model becomes really bad. Can someone tell me why? Why in this particular case, the volcano model that's been working so well for traditional data will certainly be your enemy? You were smiling, so it's indicating that you might know something. Go
I
ahead.
have an idea of how you're on.
Sure, go ahead.
My guess is because it goes up layer by layer, and so you're going to work with big data sets that don't fit in cache. But if you did, say, tuple by tuple up
Yes.
the whole pipeline, then you're not going to invalidate your cache quite as much.
Excellent. The keyword is you go tuple by tuple. It's not going to give you good cache locality. Right? If you think about it, you bring a tuple at a time to the next operator in the pipeline. Think about this as a pipeline evaluation on more than CPU. You're doing tuple by tuple, which means your cache locality is really bad. Every time you bring a cache line of data, you are looking for just one record. And that's one thing. The second thing is the volcano model, if you think about it at the macro level, is really iterative in nature, right? Tuple after tuple after tuple after tuple. This iterative process is really bad for multi-core architectures. And you're not leveraging any of the advanced features given by today's and the compilers such as SIMD. Think about the filtering operation we're doing. Find all students with record ID, student ID between 100 and 200. That's a perfect value for you to use compiler optimization such as SIMD, single instruction model data, because you are doing the same instruction, which is checking whether SID value is between 100 and 200 over multiple data, multiple records. If you vectorize your data representation, meaning you push all vector and bring the entire vector into cache, one instruction, you're done. It converts this vector into a filtered version of the same vector. Meaning get rid of those records do not satisfy your condition and keep only those ones do satisfy. So that's one instruction per this many records in that vector. Compare that to the volcano model. If there are 100 records in this vector, you need to pay 100 CPU instructions instead of just one instruction for the vectorized representation of your data. And this particular topic is called code generation. And people have been using things like, in Java, in the context of Java, people have just-in-time, Java just-in-time compilation, JIT, just-in-time compilation, or in the grand scheme of things, in the broader sense, people have been using things like LIOVM, which is a generic just-in-time compiler to optimize query plans. So keep in mind, things are changing. That means that in order for you guys to understand these more advanced topics, we do need to understand the volcano model to begin with. That's why, for the most part of this course, we will be still sticking with the volcano model. But toward the end of the second part of this course, just give you guys a heads up, I will be talking about things like this, like how to do code generation and all that, if we have time. Okay? All right, so that's that. So before I proceed, I want to give you a quick demo, not a demo, but show you a real query plan from a real database engine. Right? So if you log into our class-wide database server, and if I connect to the DVD rental database, that's part of your homework one. And let's say I want to select start from actor. Okay, let me say I want to put that off. This. Right? Just actor ID. There are many such records. But I want to see how this query is actually being executed. So you can use the keyword explain. That makes sense? And what this will do is show you the plan. On this case, it's a really, really simple plan. Just a sequential scan, key file scan. Now, let me show you a slightly more complicated plan. The first name, like this. It's also a sequential scan. However, what if I do distinct? You see there's a difference in the plan it produced. Why is that? Can someone tell me why there's a difference? What's the difference between the two queries?
No repeats on the name.
Huh?
No repeats on the name.
There may be duplicates on the names. That's why if you specify the distinct keyword, it will trigger a different plan. You need to remove that duplicate. You cannot just do a sequential scan and be done with it. You have to do a sequential scan, extract out the attribute, and remove duplicates. Now, what if I do this though? Can someone make a guess? Would this be giving you a plan same to the first plan or a different plan to the first one? Mumbling. Somebody can stand out and take a lead on this. She is saying it will be the same because actor ID is the primary key, so that you don't have to worry about duplicate elimination. But that's really a smart answer, right? Let's see whether this database server is that smart. I actually don't know. Let's see. But it's not that smart. Okay. It still tries to remove duplicates even though it's unnecessary to do that duplicate elimination. Okay, this simple example actually shows you, given how sophisticated and how advanced database engines are today, and you're paying big bucks for Oracle and all that, there are still places like this where it's pretty dumb, right? Does that make sense? Knowing that actor ID is the primary key, seeing that distinct keyword, I know I can safely ignore that. I don't have to, if I'm smart enough as database engine, given this query, I should simply generate this as my output, query. But it does not. Does it make sense? And for join, it's even more complicated. I'm sure it's way more complicated. Let me actually show you guys maybe. So toward the end of the DB, this discussion will have a couple of really complicated queries, huh? Like this. So I'm going to fix this. So remember, what this query does is to scan or search through the catalog data and find out the attribute name, attribute type for this customer table, right? So it's a join over multiple tables and fairly complicated, and we get an output like this. You may wonder how this actually is done. Okay. All you need to do is to add an explain keyword. This is pretty much like, imagine you're writing a C or Java code, and you let compiler compile your code, produce a binary code, but you want to understand what the compiler has done. Right? Are you moving my loop environment out of the loop? Are you getting rid of some branching or whatever? I want to understand what the compiler has done before I actually take your binary representation and just execute according to what the compiler is doing. Of course, typically we just take what the compiler has produced for us because compiler is so good, we just trust them 100% degree. But if in case you are curious, you're not sure whether they have done a good enough job, you want to explain what happened. This is what you do. If you look at this, this is way more complicated than the last one we have seen. This may look like you probably have no idea what's going on here, at least for now. But later on, as our discussion further along in this course, you will have, to me, this is crystal clear. It's a tree representation and tell you how to execute the join and the ordering of the join and what operator to use for each join and all that. And they even give you a cost estimation. And whenever possible, you try to use index and all that. And the whole purpose of the next few lectures is for you to understand how this is generated and how to interpret things as such. And eventually you will be implementing this in, I think in your lab 3 or 4. I think it's lab 4. You will be implementing Query Optimizer. So you will be able to produce this, the explain keyword, by your lab 4. Okay? Does that make sense? All right, so that's what we're going to do. Let's come back and continue our discussion here. So you notice from this output, they use index scan in a couple of places. The reason is pretty much like heap file and sorted file. If you have some data structure that facilitates access to your heap file and give you better efficiency, you want to do that. For example, find student with student ID equal to 100. If I tell you it's a sorted file sorted by student ID, you wouldn't be doing a sequential scan from the beginning. If you were to do that, it works, but it's fairly inefficient compared to just do a binary search on student ID. So, but leveraging on that observation, database system does not just use sorted file, which is arguably the most straightforward way of organizing your data. So database system introduce more sophisticated ways of organizing your data such that you can leverage those data structures to facilitate your query answering and operations. Okay? And that's what this index scan means for, right? But in order to understand those guys, and before we can start that discussion on query evaluation and query optimization, we really need to understand these machineries, such as index and all that. That's essentially what I will do in the next 2 lectures. Okay? And there will be a lab ask you to implement a particular indexing structure. Okay? So that's where the next few slides come from. So as I said, index is just a particular data structure to organize your heap file in a particular fashion such that answering particular type of queries will be much more efficient than to answer them over a plain heap file. Right? And to do that, we first introduce the concept of search key. A search key is not to be confused with the concept of keys for a relation, right? The concept of key, quickly recall the definition of key is you have super key, you have primary key, you have candidate key, but they are just a set of records that uniquely identify a record. Meaning no 2 records can have same values on key field, right? That's the concept of key. Search key is different. Search key has actually nothing to do with the concept of key. Search key is simply a set of attributes that you have selected to build an index over. So that means that search key can be any subset of your attributes, and they don't have to be distinct in terms of the values from the record of that table. For example, first name can be a search key. Obviously, first name is not a key for the student table, but search key, first name can totally be fine using as a search key. Okay, for example, you can sort student table by first name. Nothing wrong with that. So that's the concept of search key. And once you have the concept of search key, the way to understand index is follows. All indexes contain a collection of data entries and support efficient retrieval of all data entries with this particular form called a value k and star. So you can think about data entry as a generic representation of a data entry is that you have 2 parts. This is not a page. This is a data entry, not a page, just a data entry object. A data entry object, you can think of a data entry object as 2 parts. One is a search key value k. A search key value k. A search key of your choice. You can choose any subset of attributes of a given table as your search key. And this k is simply a possible value of that search key field. For example, if my search key is first name, then a possible value of k is for example, 50. And again, that's a possible search key value k. If your search key field is first name. But this is not going to be a possible search value, right? Search key value. For example, if your search key is first name and you say your possible key value is 18, that makes sense. At least I haven't come across a person named 18 as first name. Maybe you do. So I haven't encountered such a person yet. So this is invalid, right? And the second part of data entry is just a generic representation called heuristic. And this can be, there are 3 different choices for this. Which is what I'm going to discuss next. Okay? The 3 alternatives are, the first alternative is actually just the actual record. An actual record to be placed here, such that the search key field of that record has this particular key value k. So in other words, choice 1 is that the data entry is simply k and a record r, such that projection of your search key over r equals to k. Does that make sense? The value of this record on the search key field equal to this value k. Yes or no? And to simplify this further, if you think about this representation, this search key value k is a duplicate, a redundant information, because it's part of the record r. R is a record. You can actually ignore this part because somewhere in the value field of r you have this key value, search key value k anyway. So you don't have to store it another time. So it's a redundant representation we can safely ignore. So that's the first representation. Any question on the first alternative as you data entry? Yes or no? Are you really good? All right.
Excuse me,
Yeah.
I didn't understand.
Go ahead.
Why we are even talking about data entry. I think
You lost
the
motivation, right?
motivation.
Very good. So the reason we talk about data entry is to facilitate the construction of indexes on top of it. So you build index over this collection of data entries. So in order to understand that index structure, we need to first understand the basic element of an index. Any given index, the basic element is data entries. So we first understand data entries, then we talk about how database engine can organize the data entries to design different indexes. So that's the first representation. The second representation is the following. Once I write it out, you know you know exactly what I mean. It's a search key value k and a RID value. RID, you all know by now, stands for record ID. Can you tell me what RID consists of? Ika. Louder? It means record ID. But what's inside RID? Reference to. And to be more special, there are 2 components in RID, right? What are they?
Yeah. Oh, the.
You just implement you lab 1, right?
Yeah, and I can space it.
Someone else?
Yeah, I can space it.
Go ahead. Yeah, go ahead. Yeah.
Page ID and slot.
Page ID and slot number. Using those 2 values, you can uniquely locate that particular record. So what this tells you is, of course, you cannot use any RID value. You use RID such that the record with this RID value has projection of search key over k over r equals to k. You see how this goes, right? Essentially, you need to be able to retrieve the record with that particular search key value. That's why we use RID of that record in the data entry, so that we can uniquely identify that record with this particular search key value k. The third alternative, if you think about it, I'm going to continue here because I run out of space with it. The third alternative is that if the search key field, if your search key field is not a key of your schema, what happens? If it is not, like in this case, search key is first name, it is not a key of my student table, what may happen? Well, you may have duplicate values. Meaning, in other words, given a particular value k, like Feifei, you may have multiple records with this name, first name Feifei. Is that right? So, if you go with the second alternative, what happens? For the same third key value k, you may have multiple data entries having the same third key value k but different RID values. For example, I can have so what this means? Well, I have two records with the first name equal to Feifei. The first record is on page 10, slot number 78 from that page. The second record with first name Feifei on page 12 with slot number 10. Perfectly okay. Entirely possible. Totally impossible, right? So, but if you look at this observation, if you leverage on this observation, the worst case what may happen? The worst case you may have, I don't know, Feifei suddenly become a popular name. There are millions of Feifei, right? So I suppose there are tons of these guys. Which is fine, but you are kind of duplicating the third key value k this many times. So the third alternative is really to grab all of this and collect them into one. So if I generate this, it's not. Okay, that's the third alternative. A single third key value k and a list of RIDs for those records having that third key value k. You may wonder, wait a minute, seems like this is always better than the second approach. First of all, we know one thing, when the third key field is a key, the second alternative and third alternative have no difference. For example, if I use third key as SID, student ID, the second alternative and third alternative have no difference whatsoever because you know there will be only one, at most one record with a given third key value k. Maybe no. Maybe none of my students have student ID equal to 100, but if there is one, if there is a matching, there should be at most one matching. So second and third alternative are the same when a third key field is a key. But when it is not, like in our example, the first name, obviously there's a difference, and it seems that the third approach is always better than the second approach in terms of saving space and saving overhead. So why people still design the second alternative? There's a reason for that. Can someone tell me why? What you can think of the benefits of going with the second alternative? Any benefits? Except the answer, I just like it. You have to give me a reason. Right? You have to justify why.
Will the cost be lower?
The cost will be lower. Why? Why is the cost will be lower?
Because you're just referencing the record ID in your search key, whereas the vector is.
But that's pretty much what we're doing in the third alternative as well.
True.
So there's not much of difference in that regard. What's the key difference of the second and third alternative? There's a key difference.
Consistent space usage.
Say again louder.
Consistent space usage. The first one, each tuple is always the same amount. The second one is going to be variable.
Okay, fantastic. If you allow me to continue on the direction you are saying, to be precise, fixed length versus variable length, data entries. If you go with the second alternative, the size of your data entry is fixed length. Suppose your third key value is fixed length. The record ID is fixed length because page ID and slot number. The value can be different, but the length of it is the same. So second alternative gives you fixed length data entries, whereas the third alternative gives you variable length data entries because the list of RIDs will be different. The length of that list will be different for different third key value k. You may wonder, okay, big deal. What's so important, so significant about this? Well, you're going to organize the data entries into indexes. And the way you're going to organize them into indexes is organize them into pages. Which means if you go with the second alternative, you are dealing with fixed length objects. If you go with the third alternative, you are dealing with variable length objects. And we all know from our earlier discussion, organizing objects on a given page, fixed length is much easier. Period. Variable length is much more work, much more overhead. That's why in lab 1, I only asked you to implement fixed length record. We used to have variable length record project, but that's actually way harder to debug. You saw the discussion, right? On the discussion forum, people not complaining, but reporting that they have bugs on, miscalculating the offset values and so on and so forth. And that's for fixed length record. Imagine how bad things can be if you're dealing with variable length. The chance of it for you to have a miscalculated offset value in that case is way higher. That means that you will spend way more effort in debugging your code than fixed length. Okay, so that's the kind of the trade-off between those guys. Now I'm going to skip this slide really quick because that's essentially what I said so far. I'm going to skip all of this. And with that being said, there are a bunch of high-level points I'm trying to make for index. Instead of going over this, I think I'm going to take a slightly different approach. I will jump directly into two specific index constructions. And then once we finish the discussion of those, we come back and look at the high-level summaries. I think that's probably a more effective way of understanding the point I'm trying to make here. That means that I'm going to switch gear and jump into hash index structures. Okay, hash index structures. So, the big picture is what? Big picture is you have a bunch of data entries. They are produced new data entries. And the question is how to organize them into something that's useful for your query evaluation. Of course, you can say I do nothing about these data entries. I randomly place them into pages, which is fine, but it doesn't do much. I actually only introduce overhead to you. But why you maintain this data entries if you don't do anything about it? So you want to do something that's meaningful and useful for your query evaluation. And the first thing comes to mind is a hash-based indexing structure. And speaking of hashing, hash index structure, there are really two approaches. One is static hashing, one is dynamic hashing. Static hashing means that you are given a set of data entries to begin with, you organize them into a particular fashion, and you don't worry about updates afterwards. Dynamic hashing is that you are given an initial set of data entries, you organize them into a data structure, but subsequently you need to deal with updates. So those are, obviously, static hashing is more challenging, right? Because static hashing, you can use static hashing as a special case of dynamic hashing with zero updates. Okay? So static hashing is really, really straightforward. You use hash function h. This actually deserves quite a bit of discussion, right? What kind of hash function am I going to use? Generically speaking, a hash function is nothing else but a mapping from your input field to output field. Now this is a hash function. This is perfectly okay to be a hash function, which is take any first name value and map them to 1, a value of 1. In my view, what's the point? What are you doing here? This hash function accomplishes almost nothing. No matter what your names are, you map to a constant. Does that make sense? Well, I think it serves some purposes in some cases. For example, you want to make sure there's no discrimination against people by their first name. Then you want to hide their first name value, so everybody hash to a constant. Then in that application scenario, this is the perfect hash function. That should be exactly the hash function you use. You don't want to design a hash function such that it has to, a value from 1 to 10, depending on for example, the length of the first name. That defeats the purpose. If you do that, I may still use first name value as a basis for discrimination because once I figure out, the longer name has to a larger value and so on and so forth. Does that make sense? Yes or no? Okay. So this is perfectly okay hash function. But in our case, this is not very useful, right? If we were to take this as a hash function, you build your data entries over first name, you have a bunch of data entries, a lot of them actually. Suppose you have 1 million records. I'm assuming for now and for all subsequent discussion, unless otherwise specified, I'm going to go with alternative 2, which is 1 data entry per record. If you think about it, alternative 2 really gives you that, which is 1 data entry per record. Because it's a third key value k with a single RID. So each record will be producing a single data entry. So if you have 1 million data records, you're going to have 1 million data entries. And if I were to use this as my hash function, it's not very useful, right? Meaning no matter what your first name values are, they all be mapped to one location, and there's no way I can distinguish them. I cannot use this as my index. It doesn't really help me accomplish anything. So we need a good hash function. Somehow we can distribute those data entries into what we call n buckets. And the index value of these buckets are from 0 to n-1. By the way you should understand each of these boxes, this is a page, a single page. How many data entries a page can fit? Well, that's to be calculated using the page size. Let's say I use P for page size. And let's use, let me use a notation. Let's say E as data entry size. Both are in bytes. Then how many entries I can fit in a page? The floor of that. And this is essentially, that's the B prime. To be different from B. B represents the number of records you can fit in a page, which is calculated by P over the size of your record. If I use E as a data entry to be consistent, this becomes the size of E. One observation clearly you can make is B prime will be greater or equal than, much greater than the value of B. Why? Does someone explain this to me? Why B prime is much greater than B? Well, compare these two values. You have the same P value. Whichever has smaller value leads to a larger value at the other end. And obviously the size of an entry is much less than the size of a record. Because you are looking at just a single field of your record. Of course, not necessarily just a single field, because your third key can be a composite object, meaning several attributes. First name and the last name, for example. That can be a third key. But nevertheless, it's a subset of your record. So the data entry size must be much smaller than the record size. So as a result of that, B prime is much greater than B. Translate to human language, what that means is you can fit in many more data entries per page than the number of records you can fit in per page. Does that make sense? And to further that argument, the number of pages you need to store all data entries will be much smaller than the number of pages you need to store your records. If you use alternative 2, you have n records in total. The number of pages you need for that is n over b. If you use alternative 2, you have exactly n data entries. And the number of pages for that is just n over b prime. Because this is much bigger than this, obviously you have this relationship. That's essentially what is that. Okay, everybody follow me? It should be, you guys need to be crystal clear about all these relationships, right? Because it comes into picture later on in our discussion. Now that means that each of this is just a page with data entries. All you need to figure out is where a given data entry goes. If I were to use this hash function, what happens? Well, all data entry goes to bucket number 1. By the way, I call each page a bucket, and I use the index value to differentiate that. So bucket 0, bucket 1, all the way to bucket n-1. So far so good? Yes or no? If I were to use that hash function, what happens is all my data entries end up in bucket 1. But of course, I'm not going to use that hash function because that's an extremely bad hash function in our purposes. For our purpose. Right? So what is a good hash function in this case? Actually, let me go backward a little bit. If I were to use that hash function, which is to hash all data entry into bucket 1, what happens? What happens? Can one page be good enough to hold all data entry going to bucket 1? You said no. Why?
I think it depends on the size of the data entries.
It's dependent on the size of data entry and the number of data entry you have, and at the end of the day, you need this many data pages to store all your data entries. If you are going to use this hash function, all data entry end up in bucket 1, you need this many pages in bucket 1 to hold all of them. Which explains that linked list you see coming out of it. It's a linked list of pages. The length of this linked list obviously depends on how many data entries end up in that bucket. So if you're going to use this hash function, what you end up with is something like this. Yeah, a page for bucket 0, a page for bucket 1, a page for bucket 2, and so on and so forth. Initially, but all of the other buckets are empty, and this one is fully occupied. Each of this is not a record anymore, each of this is a data entry. And you will run out of space on this page, you end up link them together, and how many of this you have? Does it make sense? If you are going to use this hash function. Yes or no? All of you follow this? Now, if you are going to use this to facilitate the search, if I want to, for example, if I use this to facilitate this query here, what happens? What happens? Well, you apply the hash function, this hash function, over this. And now surprisingly, in this case, you got a value 1. Because no matter what the value is, you map to 1. So you go here, you do linear scan over this. Now you have data entries of different values with different search key values. You find all the data entries where search key value k equal to Feifei, follow the RD, retrieve the record. Even in this really bad organization, you still end up saving time. Why? Suppose there is only one Feifei. There is only one record with Feifei. The cost of doing this is n over b prime. In the worst case, I have to scan all the pages in my data bucket to find the entry with value Feifei plus 1 to retrieve the record. Follow the RD to find the record. Versus what happened in the other case? The worst case is N over B. You have to linear scan over your heap file. This is still much smaller than this for the reason I have argued. That make sense? So even in this really bad situation, you still end up saving a lot. What is a good situation? A good situation is you don't use this hash function. You use a hash function that goes from name, first name, to range from 0 to n minus 1. And such that there are no such overflow buckets. Everything is somewhat balanced. Each bucket has only a single page. Now, what's the query cost now become if you use this to answer this query? Can someone help me with this?
2.
Yes, 1 plus 1. You do a hash, you find where Feifei goes. Suppose hash Feifei goes to 10, what that means? You go to the 10th bucket, and you guarantee to find Feifei in this one IO because each bucket has only a single page. You follow the RD, you retrieve the record. So your total cost is 2 versus N over B. Much better. No? N over B, imagine you are in Google. N over B can be billions of pages. Right? I think with that, I will stop right here. But the challenge before I let you go is really how to avoid the worst case scenario and go with this best case scenario. That's not trivial. We will be talking about that next time.